So, we were discussing the casting processes, and I have introduced to you the ingot casting process, of course, a nutshell, giving you the essence of it, and I think I was talking about continuous casting of steel when I left you last time. The continuous casting machine has several integral parts, and I think I could list the the mold is once. The second I would say is the mold oscillation system, and I have told you the purpose of having a mold oscillation, and typically what happens is the mold, because it is carved, and if it is attached to a cam sort of a situation with a fixed radius, and if it does this kind of a movement, then it is the same trajectory that the mold traces during an upward and downward movement. Okay. Of course, you will see that the radius of curvature is pretty large in this particular case. The third is the automatic mold level controller, So, and this is very important for us because we want to maintain the scenario at a constant or a steady state. You can remember that if the mold, for example, we have the ACN here, and this is the liquid depth, okay, and we have here is a slag layer, and you can imagine now, for example, that if the mold level fluctuates, that means mold level means the level of the liquid meniscus. If it fluctuates, then what happens is the distance of separation between these also changes dynamically, and this is a very important parameter in continuous casting of steel. So, therefore, there are gadgets, okay, there are measuring equipment, sensors available, which tell us to what extent the mold level, the meniscus level is actually fluctuating, even though the mold may be doing up and down movement. So, these are water cooling. So, that is the automatic mold level controller, that is very important, and it also tells us that if the mold level fluctuates too much, that means something is going wrong upstream, okay, and one such possibility, as I have indicated, if the mold level goes down continuously, it is an indication that possibly there has been deposition of inclusions in the turn dish nozzle and so on. Apart from this, we will see that as I have drawn, so we have the strand which comes out like this, that is the strand, continuous casting strand, okay, and this strand, right in the beginning we have of course, as I have indicated, a dummy block which will close the mold, and the dummy block exactly makes this kind of a trajectory. So, as the solidification proceeds, then the dummy block is withdrawn, okay, and the casting starts to move, or the strand starts to move, the solidified strand starts to move. So, a dummy block setup is there, of course, but more importantly, we have a set of guiding and bending rolls, okay, which ensures that the strand is discharged in a horizontal, and we have this spray cooling. This I have also indicated to you during the last lecture. So, bending and guide rolls, I would say bending and guide rolls is a very important system, mechanical system. We also have automatic powder feeding arrangement. These powders are going to be replenished continuously, because the casting is going to shrink, and as a result of which a gap is going to be created. This powder which is there is actually going to be entrained, okay, and it will flow out from the bottom of the mold. That is what is So, one can continuously see that solidified powders are being moving here. So, as the powder gets replenished, okay, there should be a mechanism for powder feeding onto the surface of the liquid, and I have also indicated that what is the role or what are the roles of the powder, which is very, very important. Okay. Apart from shielding the molten metal from the ambient, apart from capturing the inclusions which are rising from the melt, apart from providing a thermal insulation layer, the mold performs perhaps the most important part, that it can regulate by using adjusting the composition of the powder. We should be able to regulate for a given operating condition the heat extraction rate, and thereby maneuver the solidification rates and the thermal stresses which generate within the mold itself. So, powder feeding mechanism is another one. So, that is we have this are continuously produced. So, there has to be a cutting device which will size the billets, blooms or slabs at periodic distance, and these cutters move along with the casting strand at the same speed, and there are various kinds of cutting devices today possible. Okay, oxyacetylene flame is one such devices. So, that is the flame actually with a flame torch, the billet or the bloom is going to be sheared into a standard size, okay, which may vary from plant to plant, could be 4 meters, could be 5 meters, and so on and so forth. So, shearing and cutting mechanism, this is also there. The dummy block system, as I have indicated. And I missed one, which is perhaps the most important. I would say that here itself I would say that I should have written here the spray cooling system. So, there are altogether 8 very essential components of the continuous casting mold, starting with the copper mold, okay, water cooled copper mold, which I have. The ACN, of course, I have not included in the whole thing. Okay, ACN is a separate part, it is a separate artifact, and the ACN connects, as we have seen, the mold along with the tundish which sits in between the ladle and the mold. The solidification takes place as I have indicated, and every caster is going to have a metallurgical length. And for example, the way I have drawn it here, so it is going to be, this is perhaps, so beyond this point, whatever I have shown here, everything is solid. So, this is the solidified crust, I would say. Let me take another shade of chalk, and then possibly I will be able to show you that. So, I do not know whether this is going to be visible or not. So, this is what is, yes, this is what is going to be this is the solidified shell, and from here onwards everything else is solidified completely. So, that's how the shell develops. Okay. So, if I take a cross section, suppose if it is a rectangular cross section bloom or billet, then the cross section will look something like this. This is the mold, and this is perhaps very thin. The mold has just that is, and I would say that I will not draw it like this. I would say this is the liquid core, and this is the boundary of the shell. And here I think I would just draw this, that this is, so that there is one-to-one correspondence between what I have drawn on the right hand side, and this is the scenario. If you take it here possibly, the shell is now a little bit more bigger or thicker. So, therefore, I would say that this will look something like this, and this is the shell thickness at the mold exit. So, and this is a very important parameter. I have indicated in the last class that the shell thickness at the mold exit must be sufficiently large, so as to withstand the hydrostatic or the ferrostatic pressure of the liquid, because you have 1 meter depth of liquid, steel has a density of 7,000 kg per meter cube. So, that ferrostatic pressure, otherwise what we are going to see, that also I have indicated that there could be bulging of the strand, and strand bulging is one such phenomena which is which can be shown here something like this, that the strand bulging can go, that this is a typical phenomena of the strand bulging, I would say. So, this is, if there is a large ferrostatic pressure, then we have so if that this kind of a scenario takes place, then there is a alarm system in the continuous casting machine, and that alarm system which is essentially thermocouple driven tells the operator to reduce the casting speed, because then what happens, the material will stay in the mold for a longer amount of time, more heat transfer will take place, and shell is going to be bigger. We must understand, I will discuss the factors which are very important, that the casting time, casting speed is a very important parameter. The speed with which the strand is taken out. Okay? So, if U represents the casting speed multiplied by the mold cross sectional area, A mold, and this is the volumetric flow rate, and that must be at steady state the volumetric flow rate of liquid from tundish, and at steady state that must also be equal to the flow rate at Ladle. This casting speed is gives us for a given length of the mold. For example, if this is L sub m, the length of the mold, then the casting speed, mold length divided by casting speed gives us a time scale which we call as the T dwell, the mold dwell time, and this is the important parameter. During the casting, once you have prepared the mold, customer has told you that it requires 200 into 200 cross section bloom. So, you have selected your bloom, you have placed it, and now the dwell time can only be changed by changing the casting speed. And we must understand that larger is the casting speed, smaller is the dwell time. So, smaller is going to be the rate of heat, total amount of heat that is going to be extracted from the mold, and as a result of which what happens is you can have smaller dwell time. Smaller means less than the required dwell time will give rise to the phenomena of bulging, as well as the extreme scenario being the breakout. Okay? Now, if you go here, for example, if you look at here, and here possibly the scenario will look something like this, and this is the scenario. Bulk of it has now been solidified. So, the progressive solidification in terms of the descending distance from the meniscus can be depicted in terms of the three figures which I have drawn here. Basically, this figure 1 is meniscus, figure B at the mold exit, and figure C is at a substance. And if you go here, this central core, which is the liquid core, that vanishes, the strand becomes completely solidified, and the distance from the meniscus is termed as the metallurgical length of the caster. Within the mold region, we only want to extract heat because of the resistance offered by the film as well as the cooling, as well as the powder. And if you look at the powder will have occupy, for example, if I can draw, this is the mold wall, and this is the water cooled mold wall. If it is copper melts somewhere around 1100 degrees centigrade. Okay? So, therefore, we can expect that the mold is not going to be above 800 or 900 degrees centigrade. On the other hand, if I draw an exaggerated figure, this represents the surface of the solidified casting. This is solidified region, and this is the gap between the mold and the solidified casting. At this solidified casting, because the mold time, dwell time is extremely small, you can imagine it is going to be less than a minute, or of the order of 1 or 1.2 minutes. So, if you take a 0.8 meter distance divided by 1.2 meter per second per minute casting speed, so you can see it is going to be less than 1 minute, actually that is the mold time. So, it is 40 seconds, 45 seconds, something like that. So, that ratio is what has been written in terms of some representative dimensions. So, therefore, the solidified material, possibly if steel is solidified, I will expect that the surface temperature will barely go above 1200, 1300 degrees centigrade, or go down, because the solidification has just taken place. It is right here that liquid steel is existing, because the thickness of the shell is very small, as I have depicted in this particular figure. So, as a result of which, what happens is, this is going to be somewhere around say 1400 degrees centigrade, this is going to be 800 or 900 degrees centigrade, and you have a powder that is filled within this part. So, it is understood that the powder may be in the liquid state if it has a melting temperature. So, the powder's melting temperature will be adjusted in such a way that it stays between the two, liquid as and the solid as temperature. Similarly, as the powder will travel within the powder is going to be liquid here in contact with the solidified casting, and then it is going to be semi liquid, and then it is going to be crystalline, and then it is going to be solid powdery form where it is contact. So, different characteristics of the powder is there. Okay. Within this film, and this distance what we are talking about possibly is of the order of 1 millimeter or less, and this distance is varying as a function of the distance of the mold, distance from the top of the mold, because the casting has shrunk more at this mold exit than it has shrunk in the top part. Okay? So, therefore, the mold is tapered to accommodate that, such that otherwise what is going to happen? The resistance to heat flow is going to be larger here, the resistance of heat flow is going to be lower. So, the mold taper is calculated by considering certain characteristic features of the solidification process, and steel casting, particularly the shrinkage of steel casting is taken into account in order to design that what should be the angle of taper in the mold itself. And the objective here is to ensure to the extent possible that the thickness of the film really does not vary from the top to bottom to any significant extent. So, the relative characteristics of the powder within this region between the mold wall and the solidified casting can vary on a case to case basis, depending on superheat, depending on casting speed, depending on the composition of the steel, because with composition the solidus and the liquidus temperature etc. will go down. The shrinkage is a function. For example, the peritectic steel does not shrink the same way as does a normal steel shrinks. So, there are because of the transformation reactions, there are phase volume changes, and as a result of which the shrinkage becomes as a function of composition, and as a result of which what happens is this gap, because the mold is fixed, also tries to change, and then the entire picture of thermal resistance changes, affecting the rate of heat loss and so on and so forth. Bending and guiding system, spray cooling zone, I have told you about this. Spray cooling zone is very important in this particular case and is an integral part, because in the mold region it is only a small part is solidified, as I have indicated in this particular figure, because we are unable to extract heat, because there is a contact thermal resistance, there is no direct contact with a cooling medium. So, the heat extraction rate is relatively weak. In the mold, our objective is to only form a sufficiently shell thick, okay, and then which can sustain the ferrostatic load, and then we can draw. Predominantly, I would say that all the superheat which is there in the mold, that gets eliminated by the circulating water, okay, and the shell thickness is extremely small. Real growth of the shell thickness, or considerable growth of the shell thickness occurs in below the mould, or once the strand, this is the descending strand of the continuous casting machine, whatever is drawn here. When the strand exits from the mould and it travels downward, it meets a number of sprays from both sides, and there the water jet or the air mist cooling, that means air water jet, comes in direct contact with the hot surface of steel, and as a result of which what happens is, large rate of solidification can be imparted on the descending strand. So, the cooling rate is small, and here the cooling rate is large, and because the spray cooling zone is spray cooling is very intense, and based on these features we call continuous casting machines have been characterized as the primary cooling zone, which is the mould region, and the secondary cooling zone, which is the spray cooling zone. And this spray cooling zone, the heat flux here is basically a heat transfer coefficient and T surface minus T water or the T jet, and spray heat transfer coefficient is really large. The heat transfer coefficient also can be enhanced significantly, because it is a very complex subject what is going on when a water jet, this is at 1400 degree centigrade. So, this is a case of boiling heat transfer actually. So, one has to understand there are quite a bit of complexity, how does heat extraction really takes place, that there is also a film, because the gas vapor forms at the surface 100, the water jet temperature may be just 30 degree centigrade, it impinges on the surface where it is 1400 degree centigrade, but here it may be 1100 or 1200 degree centigrade, and as a result of which what happens is you have a skirt of gas envelope which forms here. These are air nitrogen mixture, oxygen nitrogen mixture which forms here, and this is basically you have to understand the theory of pool and nucleate boiling in order to understand the mechanism of heat transfer. But nonetheless, this heat transfer coefficient is very large when you use air water or air mist cooling. Air mist cooling basically is a air water mixture jet, and that helps to create fine droplets, and the droplet surface area really makes the heat transfer coefficient very large. Primary cooling zone, the mould heat flux basically obeys a relationship like where T represents the time below, or we can also say that the average mould heat flux is really equal to A prime B T d, in which T represents the dwell time, and that square root dependence of heat flux in the mould region is essentially a reflection of the parabolic rate law of solidification. Okay. So, this secondary cooling zone is the zone where the largest amount of heat is going to be extracted, and the distance also is significantly larger than the mould distance itself. This determines basically the metallurgical length. This is the dominant part of the spray design is therefore critical, because that determines the length of the caster or the metallurgical length of the caster, to be more specific. Now, in the turn dish, and I have put it very easily, but running this machine on a sustained basis, producing defect free steel is a very big challenge, and it hasn't happened overnight. Okay. From the 1960s onwards, there has been significant amount of development, and as I have indicated in one of my preceding lectures, that we have not been able to yet cast all grades of steel through continuous casting on a sustained basis, which are essentially defect free, and occurrence of defects, which we will study a little later, okay, is quite sporadic in continuous casting machine, particularly if you play your cards not so well. Now, when the mould, in the mould, the heat transfer, as you can see that flux is maximum here, the flux decreases, okay, in accordance with the equation, and the flux here, because the distance time here is more, casting speed is constant. So, T is less here, T is medium here, T is large here. So, in accordance with that equation, therefore, the flux is smaller here, and that is quite legitimate, because we would expect that the the resistance to heat flow is going to be larger in this particular case, because we have a thicker shell and we also have somewhat thick air film or powder film between the mold as well as the casting surface. Now, as soon as the mold material exits from the mold, it meets the spray. So, if the spray is extremely intense, in that case what happens is that for example, there could be phenomena of what is known as surface overheating and or undercooling. The intensity of spray throughout the length cannot be same. These sprays provide a rate of heat transfer through an appropriate heat transfer coefficient such that the mold, the heat flux value at the mold exit and the first spray heat transfer rate or the first the heat transfer rate offered by the first spray are not drastically different. So, if these two rates are drastically different, if the spray is either too weak or too strong in comparison to the rate of heat extraction or the heat flux value prevalent at the mold exit, in that case what happens is we can have phenomena what is known as overheating and undercooling. Okay? Overheating if it happens, then what happens is remelting may take place. Undercooling if it happens, in that case material can unduly get into thermal stresses. It is said that all the cracks that originate in the continuous casting machine or seen in the continuous casting products actually originate within the mold itself. Mold design, powder design, casting speed, superheat, etc., are all important variables. And when I talk of mold design, mold taper, mold material, the corner of the mold, whether it is the mold is like this or the mold is chamfered here, these are the features which all determine the types of cracks, the rate of heat extraction. Faulty design of powder can lead to enormous amount of small cracks to be originated, which can manifest because it is here that intense heat transfer rates are gradually being applied. The material is subjected to mechanical stresses, and as a result of which, if any crack can originate here, that crack can propagate and grow, or has enough chance to grow and propagate in the secondary cooling zone itself. So, it is very important for us to regulate the casting parameters within the mold, and apart from designing of the correct powder, the most important parameters that I will say for a given mold is the superheat, is the casting speed, mold design and mold taper, these are perhaps the most critical factors as far as ensuring a defect free product is concerned. Okay? And superheat and casting speed, they have an inverse relationship. Okay? If your superheat is large, in that case the casting speed has to be lowered, and that is why it is very important that I have been telling you throughout my steel making lectures that there is going to be, beyond the primary steel making process, heat is going to be, because you have a secondary steel making process or a little metallurgy steel making process for about 70 to 80 minutes. So, we will require some amount of heat supply, and that is what we accomplish through the little refining furnaces. And also we have seen that we add so many of solid materials, there are wear feedings, there is vacuum degassing, drop in temperature takes place, and here is the caster operator who has told me that look, I will not accept the material if it reaches 1540 plus minus, just quoting a value, representative value plus minus 5 degrees centigrades, and because all his casting parameters, he has already designed powder, it is based on this, he has set up that what should be the casting speed. Okay? It is based on this information, the spray cooling characteristics have been, and if you now the molten metal arrives at 1565 degrees centigrade, you cannot wait because there is another ladle which is following. Okay? You have to cast it. in that case what happens is the casting speed has to be reworked, the spray cooling characteristics has to be reworked, and maybe in some extreme cases the powder composition may also will have to be reworked. So these are very important parameters, and therefore tight process control is necessary. Okay, the cleanliness of steel, as we will see later on, is also a very important parameter, but most important is perhaps in the context of continuous casting is the superheat. And superheat, you know what it is, that superheat is defined as the actual temperature minus the liquidus temperature. This difference is called the superheat. The superheat is prescribed by the caster because based on the superheat the caster has worked out all his parameters on the basis of available models and so on and so forth. So I have given you, and following this, so the cooling here is through spray cooling, and then we have the final cooling which is the radiation cooling, and which of course it is sigma epsilon theta s to the power 4 minus theta a to the power 4. Okay. So where theta s represents the absolute surface temperature, so this is the cooling, and this flux is not so small. If you calculate, the surface temperature could be in the radiation beginning of the radiation cooling zone maybe about 900 degree, 1000 degree centigrade. Okay. The material inside is still very soft, still very fragile, because it is just solidified, and if you calculate theta s to the power 4, that means 1000 plus 273, theta is the absolute temperature, is an enormous value, maybe 0.1 megawatt or something like that. So, and once after some distance, of course then the cutter is there, that cutter chops off the strand to the requisite side, and these are now moved and stacked. And this is a very important exercise now, that once the blooms are going to be taken, or the billets or slabs are going to be taken, okay, this could be outside temperature could be about 800, they are going to be absolutely red hot. Okay, so it is more than 800 degree centigrade. Inside temperature could be as much as 1200 degree centigrade, and then these pieces are lifted by crane and then stockpiled. And you can imagine on a daily basis in the stock yard, when these billets, slabs and blooms cool down to the ambient temperature, how much of heat is radiated, and there is all kinds of efforts now going on to tap that heat, radiation heat, and that is an important exercise, because that is going to reduce the specific energy consumption in the meal, and also make it in turn, make steel making in turn more green or clean steel making. We will talk about this aspect a little later, maybe in the next or the concluding lectures before I wind up this course. I want to tell you one important aspect of continuous casting that I have been telling that all the time. So this is more or less the scenario. Only thing is that if I have drawn a section, if it is a bloom, so you can imagine that the section, this section is perpendicular to the board, so you are looking through the narrow face. Okay, you are not looking through the wide face. Okay, you are looking through the narrow face, and that's possibly the kind of scenario that you are going to get. Now, plumes and slabs are very frequent blooms, and these are same geometry, as I said, that the billets are small and slabs, and these are basically where flat products. When you have to make auto body of a fridge, you will obviously buy products from an integrated steel plant, which is basically a flat product unit. Okay, integrated mills mostly produce slabs. On the other hand, special steel plants mostly produce blooms and billets, and these blooms are basically used for making crankshaft, making automotive parts, and so on and so forth. There are of course mills which are produce both the kinds of products. They are simultaneously a long product plant as well as a flat product plant. A section on a daily basis, maybe 2/3 of the heats are routed to produce slabs, or 1/3 is routed to produce the long products, billets or blooms. There is a substantial difference as far as the ACN design and the flow within the mold region is concerned, because the mold region flow is very, very important. And the challenge, because this here, this is not a big challenge, because you have, for example, in ACN, which is a symmetrical about, because these are all 200 cross section or 100 cross section, okay, it looks like a square. On the other hand, the slabs have a rectangular cross section, and that rectangular cross section, the width to thickness ratio, normal slab could be about 6 to 8, and for thin slab it is about 12, and for this could be strip could be about 30. So, if I take 200, so thickness for slab 200, and so 1200 mm to about 1600 mm, that is the conventional slab. And if we take 50 and then we make 1200 to 1500, so can make 4 times. So, this could be somewhere, this is more, I think this is about 20. If you use 1200, then what happens is this becomes 24 or something like that, 1200 mm thickness. So, 20, and then it could go up to, and this may be, I think 30 is a bit small, this could be about 60 or so, but ratio. So, the geometry, this is of our concern, that is what we are talking, conventional slabs, okay, which has a dimension of 12 to 1600, thickness is about 200, and then we look at the cross section. The cross section now is, we have a narrow face, we have a wide face, and we have an ACN here. Okay. So, from the ACN, transferring of heat here, this distance is, as we have seen here from the center, this distance could be 6 or 8 times longer than this particular distance. So, therefore, the ACN design assumes critically that I mean, we have to understand that unless and until this powder has a very important role to play, as I have already indicated, and we want that this powder has to be the one layer which is in contact with the continuous metal has to be in the liquid state, and therefore, heat has to be continuously supplied to the metal, but heat is advected in this direction. Okay, the heat fluid vector is aligned in this particular direction for a Bloom caster, but chances of it getting there, heat getting there is not so difficult, even though the direction is like this, because the cross sections are small, but that the cross section here is rectangular, and that this distance is 6 times more than or 8 times more than this particular distance, heat will not like to travel to this particular direction. So, the distribution of heat is going to be, if you use a single port kind of a nozzle for slab caster, it is not going to work quite well. So, if I draw the cross section now, for example, and make it applicable to, it is a view now, I have changed through the narrow face, you are looking into a slab caster, you are looking in this direction. So, what geometry you are going to see? You are going to see that there are 2 ports, okay, of the ACN, and these ports are directed, and these directions, okay. So, this is, you are looking at, actually this scale is represented in terms of, I would say, let me draw it correctly, this is, I think, this is the narrow face one, and if you look at the wide face one, then you will look at like this, the wide face will look like, the mold will look like something like this. Okay. So, you will have, just make it like this. This is the, so now the ACN will look like this. So, this is the ACN. So, this is the white face, and this is. So, the molten metal, unlike the Bloom caster, does not flow out vertically, but it flows out in this particular direction, and there is a requisite taper of this exit through which the molten metal flows out, and this is the slag metal meniscus, and then what happens here is that the flow pattern goes something like this. The flow pattern goes something like this. These are called the characteristic twin roll flow pattern of the continuous casting machine, the slab caster, and this has very vital role. Okay? If you make this taper too deep, then no, the flow will not turn upward. If you make it too small, or upward, then this meniscus is going to be disturbed, and if it gets disturbed, then what happens is that the slag particles can get entrapped. So, therefore, the taper is very, very important. More than the requisite amount of taper will produce a cold slag metal interface. Similarly, more than less than the required amount of taper, that means if the taper is horizontal, this is horizontal or this is upwardly directed, that is what I mean. In that case, the disturbance in the slag layer could be so enormous that droplets of slag could be entrained in the system itself. So, to keep the this is not an important issue, because in the context of bloom casters, because the blooms have rectangular cross sections, square cross sections, and these distances are barely 200 mm, so which is equal to the thickness of the slab itself. But the real problem comes on the white faces, okay, which is far away from the ACN, and there to make sure that you have adequate amount of flow, adequate amount of heat recirculation in the system, liquid slag layer which is desirable for inclusion capture and so on and so forth. So, you have to have correct taper of the ACN and this taper roughly about 15 to 20 degree downward, that is what is the taper which is predominantly used. Now, in continuous casting, you can now imagine that if the level of liquid fluctuates too much, then what is going to happen? These slab casters, you have 5 bloom casters, what is the velocity? Your throughput rate through the ACN here and your throughput rate for the ACN here are identical. Okay? Suppose they are 2 tons per minute. On the lower side, there are how many such? There may be 4 strands. Through each strand, we may have 0.5 tons. So, therefore, from the ladle 2 tons will be coming and 0.5 tons per minute per mold, that is what is going to be the net flow rate. So, 2 ton is the overall throughput rate of the ladle continuous casting machine, okay? And if you have 4 such bloom casting molds, through each mold you have 0.5, and if you have similar dimensions of the ACN, in that case the flow velocity, and here you can imagine the net 2 tons may be flowing through one single mold, or in the worst case it be in a better case when 2 molds are connected, it is going to be 1 ton per minute per mold. So, the velocities are going to be really double here. Okay? So, and that velocity, intense velocity, is necessary in order to help this jet reach here, bifurcate into 2 parts, and whereby a portion of the heat can be taken to the top surfaces. Now, this taper etc., they work for a given thickness, but if you keep on, today the increasing tendency is to produce slabs which are not 1200, not 1800, not even 2200, even more than that, close to 3 meter wide, 9 feet wide slabs are being prepared, okay, or manufactured, and in that case this kind of one single taper or 2 nozzles may not work. So, then this development, ACN development, because the customers' requirement are changing on a daily basis, they want different products, more and more versatile products, and as a result of which to ensure that we produce defect free casting on a sustained basis, the design of the ACNs, particularly with respect to slab casters, has been a continuously evolving field. And as I have indicated, this mold entrapment, mold powder entrapment is a very important aspect, particularly in slab casters, and this happens when the ACN, this depth is also very important. This depth is called the ACN submergence depth. It is a very important parameter, and I think I will list here. I have given you 4 or 5 items, that what is the superheat I have written here, what is the casting speed I have written here, mould taper and mould design I have written here, and powder powder characteristics, and on top of that I think one should add that during the continuous casting procedure, because this is a parameter which of course ACN lengths are fixed, okay, because ACNs are ordered by the steel maker to a refractory industries on a bulk basis. So, you cannot change ACN designs on a daily basis or even on a monthly basis. So, these are fixed, but the meniscus level you can adjust, okay, you can bring it down, you can take it up, okay, you can decide depending on your casting speed and operating conditions, etc. And what I said, that if this distance ACN submergence depth is too small, you are going to land up to many problems in a continuous casting machine. The defects in continuous casting products are many, and of this most important ones are cracks. You must understand that even though there is a mechanical bending of the strand here, there are mechanical stresses being applied on the continuous caster, the cracks originate, as I have indicated, in the mould region itself. So, the cracks in continuous casters are basically related with the initial stage of solidification and with the heat transfer characteristics of the mould, okay, within the mould. And cracks here are a function of the high temperature strength of the steel that is you are going to cast. So, it will vary from steel to steel or grade to grade. And these cracks have various types of cracks. Corner crack is very important or frequent, corner crack, longitudinal crack, and then transverse, all kinds of cracks. And corner cracks basically occur because of faulty mould designs, that you have two dimensional heat extraction rate. So, the heat is being extracted in the corner region too rapidly, okay, and as a result of which the corner of the billet or bloom sharp, particularly cracks can originate here. That is the way the cracks. Longitudinal cracks, on the other hand, if you have the strand like this, so you can have crack like this. Transverse crack, you can have, if the billet is like this, then you can have transverse cracks like this, transverse cracks like this. And all this cracks originate either because of a faulty powder design, or because of a faulty mould design, or because of erroneous casting parameters. And of course, in the context of all such variables, the composition or the characteristics of the steel being cast also plays a very, very important role, because the high temperature strength of steel is a function of its composition. Apart from cracks, we can have the same kind of a pinhole porosities could be there. These are related with hydrogen, okay. Then we can have inclusions which could also be there, and most important here is the powder entrapment. And if you study the inclusions in continuous casting products, and as I have been telling repeatedly, that if you can locate traces of sodium and potassium, we should be able to tell that these inclusions have exogenous origin and have come because of the entrainment of thrombodity is another important, and this is because of poor mould material. The mould is, as you can see, the mould, I have indicated here in the figure that I have drawn, that the mould wall could be at 800 degrees centigrade, 900 degrees centigrade in contact with the circulating water. So, the face which is face of the mould which is in contact with the powder could be about 800, 900 degrees centigrade, and the strength of this mould material is a function of its purity. Okay? So, if the copper is not of good purity, in that case what happens, the mould will tend to soften at high temperature, and as a result of which the ferrostatic pressure, okay, will try to put stress onto the mould, and which is now weak because it is impure, okay, and as a result of which, because its high temperature strength is going to be smaller, and therefore the mould is going to deform, and you have used maybe a square cross section mold, but at the end of the day this mold may become something like this. One such possibility is there. It can have a value a rhombus kind of a shape also, and from there only. So, the distortion of the mold. So, rhomboidity is one class of defects in the. So, you wanted to produce a square cross section geometry, but your cast geometry has changed. It is no more a geometry, and it has happened because of the deformation of the mold. And one such characteristic deformation is the rhomboidity, which is very frequent in continuous casting machines. So, these are mostly the defects which originate in continuous casting machines, cracks, pinhole porosities, inclusions, as well as rhomboidity. Beyond continuous casting, we also have other processes that comes particularly under the stages of new development. But before I address that, I want to mention one important thing, that as I have indicated here, that the flow rate through the ACN in bloom casting, because the geometry and the number of the molds is small. So, the stirring here is not quite adequate in the bloom casting system. On the other hand, in the slab caster, because the flow rate is high and that the ACN dimensions are not drastically different, the velocities are going to be really very high. So, therefore, there is we cannot reduce the velocity, because the moment we reduce the velocity here, the throughput rate has to be reduced and the plant productivity will go down, but that is not desirable. So, therefore, we say that we have in this particular case to slow down the flow. The flow, as I said, the flow intensity of the flow is very important, because it can create a lot of problems. Okay, it can create an inclusion, different waves formation, slag droplets and entrainment. Then lot of remelting can take place because of, and this I have put it very nicely, and this may not remain like this, because these are refractory artifacts. They may develop defects, there may be deposition, and the flow may happen to be biased. Suppose if you have deposition taking place on this nozzle because of some irregularities, etc., flow will try to predominantly go and through this, and as a result of which this characteristic twin roll pattern is going to be disturbed. Okay? And then what happens is more amount of liquid flows comes out through this, and therefore it strikes the wall with more force. Okay? Or the solidification, front end remelting, etc., can take place. So, there is a need to slow down the velocity in the bulk of the system, and to slow it down we have what is known as electromagnetic breaking. And here is the other way around, because the flow rate is going to be smaller. So, we have electromagnetic stirring. Okay? This helps to homogenize the bath, this helps to break the long crystals, okay, make them more uniform, and here the velocity fields are dampened. So, the velocity fields are enhanced, okay, in order to promote homogenization, eliminate segregation, and so on. In this case, the electromagnetic breaking, and this electromagnetics basically happens because you apply electromotive forces. You have huge magnets, they are installed around the mold, and these magnets there is a what is that called? That's called the Lorentz force. Okay, so when you have there is a current carrying when you pass currents, and the magnetic lines of forces develop. So, the current intensity as well as the magnetic field intensity, these are two vectors, they interact, providing a resultant force which acts on a liquid like steel. It will not act like in aluminum or copper because of the magnetic properties of the materials. So, this basically the J cross H, that is the Lorentz force, both are vectors. So, you have to take a vector product, and there is going to be some amount of stirring, and in this case the stirring forces, the J cross H forces would be designed in such a way that it will have a dampening effect on the overall flow of liquid without affecting the flow rate. And similarly, in this particular case we will have electromagnetic stirring. The J cross H is going to be assisting the flow. Okay? The flow in this direction is constant, that is the casting speed. So, if the flow is to be changed, it is to be changed along this particular cross section itself. So, these are very popular techniques for controlling and the finer properties of steel which are being produced by continuous casting machines. Beyond this, we have thin slab casting as I have indicated, as well as twin roll casters. And thin slab casting, the mold design is a funnel shaped design, and the ACN design is also that's the kind of this is a thin slab mold design. Okay, the ACN design is also completely different. Okay, so these are evolving areas, and sometimes they work, sometimes they produce defects. And when you have twin roll caster, that twin roll caster basically we have strip caster. So the pool of molten metal, and the moves like this, and the strip comes out. So this is the pool of molten metal. But very interesting that here the dwell time or the contact time is of the order of milliseconds, that how within that milliseconds really heat is extracted, so that you can have solidification is a very important aspect of the strip casting machine. And inside the roll, really the engineering is at its best, and one can see that what are the mechanisms which really are in place such that which can facilitate such a large rate of heat extraction for withdrawing the superheat and bringing it below the liquid solid as temperature, even for such a small time contact, etc. But I think in a course like this, we do not have much time to discuss the details of these new advanced technologies. Strip casters, very few plants have strip casters. There is none as of now in India, but there is a discussion going on in 2 of the private plants I know. Thin slab casters are of course there in many steel plants. For example, Tata Steel has, JSW Dolvi has, also I think that Nippon Steel and ArcelorMittal, that is the SR plant, also has the thin slab casting machine. So it is pretty standardized by now. It has not yet been standardized. People are really, it's a big investment, and I think it goes very well with electric arc furnace in our effort to produce what is known as endless strip casting or endless strips. So we will continue, and I think we are at the last lecture. So we will discuss a few important other parts of iron and steel making, and then we will try to wind it up.